Let's have a look at this shear and bending stress review problem here. And that's in the test review downloads down towards the bottom, I think. And that's the shear and bending stress review problem. I've also got the key right here. All right, now let's kind of take a walk through this. Now, this is a good review for the final exam, for some of the material that will be on the final exam. So, I think it'd be best to approach this of you working through it, and then just we'll kind of go through the solution. So, I think it'd be best for anybody watching this to actually do it themselves rather than just watching me do it. You'll just get more practice and have a chance to kind of think this stuff through a little bit. All right, so what you want to do there is what we have here is we have a beam with a loading pattern shown on it. And the goal here is to find the shear stress at point B1 and also to find the maximum tensile and compressive stresses in the beam. So the first thing you would do would be to find the reactions. So why don't you see if you can take that beam and find the reactions. All right, and you can pause the recording and find those so you can check back in here and we'll go through them. All right, so here we go. Here are the reactions. So what you're going to do on this would be sum moments. Now what I did on this thing was I sum moments first about A. So I've got the 6,000 newtons per meter over an 8 meter span. 6 and 2 make 8. The centroid for the load will be right there, 4 meters over half of the 8. So that would be 4 meters over. That's the moment arm. That would come around clockwise, so that's a negative. Then you've got this couple here of 96,000 Newton meters. That's counterclockwise, so it's positive. Notice that even though we've got the location of it marked, you don't use a moment arm on that. The moment arm is already embedded in it right there with the meters. All right, and then you've got plus 8 times RD. And so then you can work through that and solve for RD. It's 12,000 newtons. Now, I'm going to build a shear moment diagram here. So the next step, I took a second moment equation about D. All right, and I need both reactions here to kind of check my shear and moment diagram, and I want to be quite sure that I'm doing them correctly. So I'm going to do 2 moment equations, and then I'll do a force equation to check my work. That's what I'm doing here. I want to be very careful here that I get the proper reactions to start, because if I get incorrect reactions, the whole shear and moment diagram process just doesn't work out well at all. So that's why I'm taking this approach. It'd be quicker just to go sum of Fy and find RD that way, or excuse me, RA that way. But I'm going to do it this way just to get a check on my work, just to be sure that I'm getting the proper shear and moment. Okay. So what I'm going to do there, I'm going to take moments about D, set that equal to 0. Once again, I got 6,000 newtons, and that should be per meter on these. I got a little bit of a typo there, don't I? Times 8 meters, and then a 4 meter moment arm. Now this one's positive because it's coming around counterclockwise. I add in the 96,000 Newton meters also, and that's positive as well. And then I'll subtract off 8 times RA. Okay, 8 RA there, that would be clockwise, so that'll be minus 8 RA. Okay, solving for RA, I get 36,000. Okay, now I've got the 2 reactions. Now I can just run a sum of Fy equation just to kind of as a check here. So if I go sum of Fy equals 0, I'm going to have that 6,000 newtons per meter, and that's going down, so it gets a negative. That's over the 8 meter span. And then the couple will not contribute to the force equation because the couple doesn't cause a force, it's just a pure twist. So I'm going to have 6,000 newtons per meter negative because it's down over the 8 meter span, and then I'm going to have the 2 reactions up. And I just want to check and make sure that that ends up equaling 0. Okay, and sure enough it does. So that's good. Okay, so that does equal 0 on that check. So I'm pretty confident that my reactions are right. All right, so now once you've got the proper reactions, you want to draw a shear diagram. So once again, why don't you pause and draw up a shear diagram. All right, let's have a look at the shear diagram here. What we got a 3,600 Newton reaction at A. That'll take our shear diagram from 0 up to 36,000. Then we can find the area under the load diagram there. So that's minus 6,000 times 8. It's negative 48,000. So that will be the change in shear. That will drop the shear down to negative 12,000. And then this reaction will push it back up to 0. So there's the shear diagram. So notice that the couple there doesn't have any effect, any direct effect on the shear. It does affect the shear a bit because it helps to cause these reactions, and that of course affects the shear diagram, but it doesn't have any direct effect on the diagram. All right, now we can see that the shear diagram is zeroing out at 6 meters over. So what we're going to want to do here, now we could check that by taking the value of shear over here, which again equals this reaction, and that's 36,000. Then it's dropping by 6,000 newtons per meter. So, and that should equal 0. So the slope is 6,000 newtons per meter. If that runs 6 meters, that will drop by negative 6,000 times 6, which is negative 36,000. That will get us to 0 at 6 meters out. All right, so we'll find the area of both triangles. On the left, we've got a positive 36,000 times 6, which is the base. The 36,000 is the reaction, 1/2 because it's a triangle. That's 108,000. On the right, we've got 1/2 times negative 12,000 for this value on the shear diagram, times the span of 2, so that's negative 12,000. Okay. All right, so once you have those areas, how about drawing up the moment diagram? So once again, you could pause and we'll have a look at the moment diagram. All right, let's have a look at the moment, and that's going to be based on the areas of the shear. Okay. So what we're going to have is the moment diagram. The change in the moment is equal to the area under the shear diagram. So that first change in moment there is 108,000. That starts at 0 on the left and goes up to 108,000. Now the slope will be very positive here. It'll be positive 36,000. By the time you hit this point, the slope of the moment diagram, which equals the value of the shear, will be 0, so it'll flatten out. Okay, what happens next there is you have that couple of 96,000 there. Now that's going to cause an immediate change in the moment diagram. Now the moment diagram will change in the opposite direction of the couple. So the couple's positive. Okay, so if you kind of look at that section of the beam, you've got that counterclockwise 96,000 couple. Well, what the beam is going to do to react to that, which is really what we're plotting up, it's going to react in this direction, and that's a negative couple. So so you go in the negative direction, you use the sign opposite of the applied couple to get on your moment diagram. Okay, so we got a positive 96,000. We change by negative 96,000 to go from 108 down to 12,000. Okay, so that drops down there. Then you have a change in moment further that equals the area under the shear diagram, and we found that to be negative 12,000 right there. So that will change the moment by negative 12,000, bring it back to 0, which it should. These shear moment diagrams should always close to 0. Okay, so there's the moment diagram. Now we want two values off of this that we'd like to get. I've got spaces for them in the handout. The first value we'd like would be the maximum moment, and there it is. It's 108,000 Newton meters. The other thing we'd like would be the value of shear at point B, because we're going to find the shear stress at point B1. So we want the value of shear at point B. So what that is 36,000 minus the slope, which is 6,000, because the slope's negative, so we're taking that as a minus. And then multiply that by the location of B, which is 2 meters over. So what you'll get then will be the shear at B, and that'll be 24,000. So that's the value of shear at B. Okay. All right, so now we've got the shear moment diagrams drawn and found the value of shear and moment that we're looking for. All right, now the next thing to do is to find the centroid of the beam cross-section. So you've got a sketch of the beam cross-section. Why don't you see if you can find the centroid? So you could pause the recording and give that a run. Okay, let's have a look at how to get the centroid here. What we're going to do is break this beam up into two pieces, above and below that 4 centimeter height there. So we're going to get the areas and the y-bar distances. Now we're going to measure from the base to the centroids of the areas. So we want to remember that. We're measuring from the base and working our way up. Okay, so that's what we're doing. All right, so, and we also want to find the areas here. Okay, so we're going to find the centroid now, so let's give that a run.